ओके, तो वैलेंस बॉन्ड थियरी, वैलेंस बॉन्ड थियरी के पहले हम इसके पोस्टुलेट्स करते हैं। कि वैलेंस बॉन्ड थियरी किसके लिए होती है? अगर हमने मान लिया प्राइमरी वैलेंसीज सेटिस्फाई करनी है, वर्नर्स कोऑर्डिनेशन थियरी में हमने किया था प्राइमरी वैलेंसीज, तो जो सेंट्रल एटम है उसको क्या करने पड़ेंगे, रिक्वायर्ड नंबर ऑफ इलेक्ट्रॉन्स लूज करने पड़ेंगे और उसको वेकेंट ऑर्बिटल्स क्रिएट करने पड़ेंगे। ठीक है, और ये जो वेकेंट ऑर्बिटल्स हैं वो क्या करेंगे, हाइब्रिडाइजेशन। प्राइमरी वैलेंसी का मतलब ऑक्सीडेशन स्टेट, तो जो भी उसकी ऑक्सीडेशन स्टेट है मेटल की, मतलब उतना उसके ऊपर प्लस चार्ज है मेटल के ऊपर, तो जो प्लस चार्ज है उतने इलेक्ट्रॉन वो लूज करेगा सेंट्रल एटम, और लूज करने के बाद वेकेंट ऑर्बिटल्स क्रिएट होंगे, और वो जो वेकेंट ऑर्बिटल्स हैं उनकी होगी हाइब्रिडाइजेशन, एंड देन वी गेट द डिजायर्ड शेप टू द कॉम्प्लेक्स। तो ऑर्बिटल्स कौन से इन्वॉल्व हों और कौन से टाइप की हाइब्रिडेशन होती है तब, और शेप क्या होती है, दैट वी विल डिस्कस नाउ। मान लिया एक S है और एक P है, मतलब एक 4S और एक 4P, अगर ये दो ऑर्बिटल हम इन्वॉल्व करते हैं तो हाइब्रिडेशन हो जाएगी sp और उसकी शेप हो जाएगी लीनियर। और अगर एक S और 3P ऑर्बिटल्स जो हैं वो इन्वॉल्व होते हैं अगर हाइब्रिडाइजेशन में, तो हाइब्रिडाइजेशन हो जाएगी sp3 एंड शेप इज टेट्राहेड्रल। सेम अगर एक d ऑर्बिटल है और d देख लो 3d, एक 4s और दो 4p, तो हाइब्रिडेशन हो जाएगी dsp2, एक d एक s और दो p, so dsp2 hybridization and shape is square planar. Now if we have two 3d orbitals, one 4s orbital and three 4p orbitals, then hybridization is d2sp3 and shape is octahedral. And again if we have one 4s, three 4p and two 4d, see in the first case there are two 3d orbitals and in the second case there are two 4d orbitals. Hybridization is sp3d2, first is d2sp3 and second one is sp3d2. What is the difference between these two we will discuss in the next part, that is CFT and VBT, and both are octahedral. So in this way orbitals involved and type of hybridization decide the shape of the complex. Now if n-1d orbitals are involved in the hybridization, then these complexes are called inner orbital or low spin or strong field ligand complexes. See, when we have 3d, 4s and 4p, that means 4s and 4p, if n is taken as 4, then n minus 1 is 3. So if n minus 1 d orbitals are involved, that is hybridization is d2sp3, then that complex is called inner orbital complex or low spin complex or strong field ligand complexes. We will discuss this in detail. So what happened in the presence of strong ligands? Electrons are grouped, they paired up against the Hund's rule, and that's why spin is lowered. And if nd orbitals are involved, then complexes are called outer orbital or high spin complexes. So when ligands are weak, then electrons are not paired up. Okay, and that's why we get sp3d2 hybridization. So what do you mean by paramagnetic nature? Paramagnetic substances are those substances which have unpaired electrons, and when they have unpaired electron, they are attracted by the magnetic field, and that is called paramagnetic nature, and it is due to the presence of unpaired electrons. And if all the electrons are paired, then that is called diamagnetic substances. So let's take an example of CONH3 plus. So geometry, you can see what is the coordination number of this complex? What is the coordination number of the metal? It is 3 is the primary valency. 3 plus is yes, 6 is the coordination number, right? So when coordination number is 6, so its geometry is octahedral. Okay, so and hybridization is either D2sp3 or sp3d2. So cobalt ion here is in the +3 oxidation state. Why is it so? Because you know that CONH3 3 plus. So in CONH3 3 plus, oh sorry, CONH3 3 plus. So cobalt ion is in plus. Oh, okay. Wait, cobalt is in +3 oxidation state. Now is it okay? Okay, and has electronic configuration 3d6. So wait 1 second. It is okay. So oh my god. एक मिनट बेटा वेट करना है. Okay. So cobalt is in +3 oxidation state and has electronic configuration 3d6. And you know cobalt is, what is the atomic number of cobalt? It is 27. So it is 3d7 4s2. So when 3 electrons are lost, then it becomes 3d6. So in this way, cobalt 6 electrons. See, 5 electrons first we fill according to Hund's rule, and then electron pairing takes place. So it is the filling as per Hund's rule, right? Now it is 3d, 4s and 4p. So 4s and 4p orbitals are vacant, but 3d has total 6 electrons. Now hybridization of this complex is D2sp3. Why is it so? Because ammonia is a strong ligand, that we will discuss in crystal field theory. But here, because 6 electrons are there, these 3 orbitals are filled in the paired form. See, 3d6. So total 3 orbitals are filled by those 6 electrons. Now we have 2 d orbitals, 1 4s and 3 4p orbitals which are vacant, and these 6 orbitals undergo hybridization, that is d2sp3, and therefore okay, so please, here there is a s orbital as well, okay, d2sp3. So in this way, okay, now is it clear? Okay, these are d2sp3 hybridized orbitals, and each orbital overlap with ammonia molecule. The 6 pair of electrons comes from 6 ammonia molecules. These 6 pairs denoted by cross sign, X sign, these are donated by ammonia molecules. So that's why complex has octahedral geometry, and you see all the electrons are paired. There is no unpaired electron, and that's why this complex is diamagnetic in nature. So when this complex is formed, inner d orbitals are used, and that's why this complex is called inner orbital complex. See, when these ammonia molecules are not joined, see, what is the spin of this molecule? See, there are 4 unpaired electrons, and each unpaired electron contribute plus half spin. So total spin of CO3 plus configuration is 2, because there are 4 unpaired electrons. When electrons are paired, then total spin is 0. See, plus half and minus half, 0, and 4 unpaired electrons. So 4 into plus half. So total spin is 2 when ammonia molecules are not joined. But when ammonia molecules donate the electron pair, electrons are paired up, and therefore inner orbital complex is formed. It is also called low spin complex. Why is it so? Because now spin is 0. So it is diamagnetic, low spin complex, inner orbital complex, or we can say spin paired complex. Now come to COF6 3 negative. Now in case of COF6 3 negative, actually fluoride ion is a weak ligand. So in case of fluoride ion, it is paramagnetic, because now pairing does not take place. Pairing takes place only when strong ligands are there, like CO, cyanide, NO2 negative, NH3. These are strong ligands. Even EN. But fluoride, chloride, bromide, iodide, these are weak ligands. So weak ligand, in case of weak ligands, pairing does not take place. That's why there are still 4 unpaired electrons, and to get 6 orbitals we use 1 4s, 3 4p and 2 4d orbitals. So it forms outer orbital complex, COF6 3 negative. Now let us take an example of NiCl4. Now just now I told you fluoride, chloride, bromide, iodide, these are weak ligands. So in case of weak ligand, pairing does not take place. So nickel is in +2 oxygen state here. So configuration is 3d8. So we will write it like this. And 1 4s and 3 4p are vacant. So see, we have 4 orbitals, and at the same time this ligand is weak, therefore pairing does not take place. So to get 4 pair of electrons from chloride, these electrons are donated to 1 4s and 3 4p orbitals. So it undergoes sp3 hybridization. So we get these sp3 hybridized orbitals of nickel 2 plus. So these 4 orbitals, 1 4s and 3 4p orbitals, undergo sp3 hybridization, and these hybridized orbitals gain electron from chloride ion, because chloride ion donates a pair of electrons, and therefore we get high spin complex. And hybridization is sp3 and shape is tetrahedral. And again we see there are 2 unpaired electrons, therefore it is paramagnetic. Now let us take example of NiCO4. So NiCO4 is also tetrahedral, but it is diamagnetic, because in NiCO4, CO has 0 charge. So obviously nickel NiCO4 is neutral, CO has 0 charge. So what is the charge on nickel? It is also 0. So nickel is in 0 oxidation state, and it contains no unpaired electron. Now let us take an example of NiCN42 negative. Again, see, it is just like NiCl42 negative, but condition is, in that case there is chloride, here it is cyanide. Chloride was weak ligand, and now cyanide is strong ligand. So when it is strong, pairing takes place. There are 8 electrons. In free state, it has 2 unpaired electrons, but when cyanides are approaching nickel, pairing takes place, and therefore hybridization is dsp2, and shape is square planar. So NiCl4 negative 2 negative is tetrahedral, paramagnetic, but NiCN42 negative square planar and diamagnetic. So in this case, cyanide ions, each hybridized orbital receives a pair of electrons, because cyanide ion donates a pair of electron. So inner orbital, low spin, or we can say spin paired complex is formed. And compound is diamagnetic, because there is no unpaired electron. Now, what are the limitations of valence bond theory? See, first of all, most of the coordination compounds are colored, like copper sulfate. Aqueous copper sulfate is light blue. Aqueous ferrous sulfate is light green. So these colors could not be explained by valence bond theory. Why the complexes are colored, it could not explain. Valence bond theory could not explain. Second, it could not explain magnetic data of the complexes. It could not account for spectrochemical series. Here we have discussed that cyanide is a strong ligand, chloride is a weak ligand, but valence bond theory could not account for this behavior. there is no mention about the weak or strong ligands. Why pairing takes place? अभी भी आपके दिमाग में क्वेश्चन होगा, why the chloride, in the case of chloride pairing does not take place, but in case of cyanide pairing takes place. Why is it so? That could not be explained by valence bond theory. It is explained by crystal field theory that we are going to discuss just after this. Yes, it does not give any quantitative interpretation of the thermodynamic or kinetic stabilities of the coordination compounds. Actually, when strong ligands are attached to the metal, coordination compound is stable. When weak ligands are attached, stability is less. So that is the case of spectrochemical series. And what is spectrochemical series? It is the arrangement of the ligands in the order of their strength. And these could not be explained by valence bond theory. See, it does not distinguish weak and strong ligand, because valence bond theory could not tell us anything about the strength of the ligand. It could not explain spectrochemical series, so it is sure that it does not distinguish between ligands. So what is the hybridization of NiCN4 K2 NiCN4? Yes. Just now we have done. Cyanide is a, yes Arush, it is strong ligand or weak ligand? Hello? Arush? Yes, Arush. What about cyanide? Is it strong ligand or weak ligand? Hello? Cyanide, is it a strong ligand or weak ligand? Cyanide is strong ligand. So cyanide, pair up the electrons. And what is the coordination number of this complex? 4. So if coordination number is 4, it is either sp3 or dsp2. So out of sp3, yes, very good, it is dsp2. Now what is the hybridization of CONH3 6Cl3? Yes, its coordination number is 6. So yes, but total 6 means we should have 6 orbitals. Either it is D2sp3 or, yes, or sp3d2, but ammonia is a strong ligand, that's why it is D2sp3. Ji, yes, please. Okay. Now next is crystal field theory. ओके, तो क्रिस्टल फील्ड थ्योरी ओके। सो क्रिस्टल फील्ड थ्योरी, इन क्रिस्टल फील्ड थ्योरी इलेक्ट्रॉन पेयर्स जो होते हैं लिगेंड्स पे, दे आर treated as point negative charges. They are point charges which are interacting with d orbitals on the central metal. And in case of crystal field theory, we consider the nature of the bond between the ligand and the metal, that is purely ionic. In case of valence bond theory, it is considered as purely covalent. But in crystal field theory, the bond between the ligand and the metal is purely ionic. We ignore the covalent bonding. That is the basic flaw of this theory. But it is very, very important in explaining the spectrochemical series, and only this theory could explain why there is a pairing of electron or there is no pairing of electron. So see, when we look at the shapes of d orbitals, dx square minus y square and dz square, in this case lobes are on the axis, but in dyz, dzx and dxy, lobes are in between the axis. Lobes are in between the axis. So these are there are two types of d orbitals actually. In free metal ion, they are degenerate metals. In free metal, d orbitals have same energy. All the 5 d orbitals have same energy. But if we look at the shapes of d orbitals, then there are two types of d orbitals. One whose lobes are on the axis. So कौन से हैं वो? dx square minus y square. In this case, lobes are on the x and y axis, and in dz square, lobes are on the z axis. And in case of dyz, dzx and dxy, lobes are in between the axis. In dyz, lobes are in between y and z axis. In dzx, lobes are in between z and x axis. In dxy, lobes are in between x and y axis. So ligands, as we view them as a point charges, they are at the corners of an octahedron. So they affect these d orbitals differently. Why? Because d orbitals shapes decides the effect. Because if we talk about dz square, ligands and lobes in octahedral field, ligands are on the axis. See, this is octahedral arrangement. Ligands are on the axis. So in dz square, lobes are head-on to the ligands. D orbital lobes are head-on to the ligand, and in case of dx square minus y square, again lobes and ligands are head-on to each other. They are on the same axis, and therefore ligands, they interact more with the orbital lobes, and therefore they result in a strong repulsion. And you know, when repulsion takes place, energy increases. And in case of dx square minus y square, dyz, sorry, in case of dxy, dyz and dzx, lobes are in between the axes. So ligands, they come in between the orbital lobes, and therefore there are weak repulsions. There are repulsions but weak. But in case of dx square minus y square and dz square, ligands and lobes, there is a strong repulsion between them. So that will split these d orbitals into two parts. One, dz square and dx square minus y square, there is strong repulsion, and dxy, dyz, dzx, there is weak repulsion. That's why these orbitals, that's why it is known as crystal field splitting. So repulsion between the ligand lone pairs and d orbitals on the metal, that results in the splitting of the energy. See, in this way, these two orbitals, dz square and dx square minus y square, they are known as Eg. dyz, dzx and dxy, they are called T2G. Keep in mind, one is Eg, other is T2G. These orbitals whose lobes are in between the axes, they are known as T2G, and those orbitals whose lobes are in between on the axis, that is dz square and dx square minus y square, they are known as Eg. So when it split, see, d orbitals in free metal ion, and if the repulsion due to all the orbitals is equally repelling all the d orbitals, so average energy of the orbital is, this is average energy. But you know, the d orbitals whose lobes are on the axis, they are more repelled, there is strong repulsion, therefore their energy is more. These two orbitals, dx square minus y square, dz square, known as Eg, and dyz, dzx and dxy, these three orbitals are lowered in energy because there is a weak repulsion, and they are called T2G. But this dotted line, this is called barycenter. Barycenter means average energy of the orbitals in spherical crystal field, and this splitting is in octahedral field, because in octahedral field ligands are on the axis. So those orbitals whose lobes are on the axis, they are more repelled, and those orbitals whose lobes are in between the axes, the repulsion is less, and therefore that difference between the energy of these two set of orbitals, T2G and Eg, is called delta O, that is crystal field splitting energy for octahedral complex. And increase in energy is divided into two orbitals, and decrease is divided among three, and therefore increase is plus 3 by 5 delta O, and decrease is 2 by 5 delta O per orbital. Now in case of tetrahedral complexes, so when we see the shape of or arrangement of ligands in tetrahedral field, and you know, in case of octahedral arrangement there are 6 d orbitals, and in case of tetrahedral there are 4. That's why d orbital splitting in tetrahedral complex is less, but d orbital splitting is inverted in case of tetrahedral. Why is it so? Because in tetrahedral complexes ligands are in between the axes. Just keep in mind, in octahedral complexes ligands are on the axis. In tetrahedral ligands are in between the axis. Ligands are in between the axis. These are the ligands. Oh, yes.
Most of this, was it not covered in spectrochemical series?
This part is called, this is splitting of orbitals, right? Split. Okay. Which one? This part? Oh, okay. Okay. We have explained it earlier. We have done it. Okay. So ligands are on the alternate corners, and therefore there is reversal, means inversion, but G sign is omitted. It is E, and in tetrahedral it is T2 and E. And this energy difference between these two sets is called crystal field splitting in tetrahedral field. So splitting in tetrahedral complexes is obviously less than in octahedral, and it is 4/9 delta O. Okay, up to this we have done, right? So magnitude of the crystal field splitting, that depends upon the field produced by the ligand, and at the same time it depends upon the charge on the metal ion. If field produced by the ligand is strong, then delta O is large, and if charge on the metal is high, then again delta O increases. So some ligands are able to produce strong fields. So in that case splitting will be large, and other produce weak fields, and therefore there is a small splitting. So those which produce large splitting, they are called strong ligands, and those produce small splitting, they are called weak ligands. So in general we arrange them in this series. See, in the starting there are iodide, bromide, sulfide, thiocyanide, chloride, nitrate, fluoride. These are the weak ligands. And on the top there is CO, cyanide, NO2 negative, EN, ammonia, pyridine, NCS negative. Means water is considered as a weak ligand. So all the ligands before water, they are all weak ligands, and after that they are considered as strong ligands. CO is strongest, cyanide, NO2 negative. So this is called spectrochemical series. This is the arrangement of ligands in the order of increasing field strength. So according to crystal field theory, electronic configuration of complexes, that depends upon crystal field splitting. In octahedral complexes, 3 orbitals are of lower energy. Which 3 orbitals? T2G. And 2 orbitals are of higher energy, that is EG. And according to Hund's rule, electrons occupy a set of orbitals of same energy, one at a time, with their spins parallel. Means electron pairing does not take place until and unless each orbital of same energy occupy one orbital with parallel spin. So for complexes having up to 3 d electrons, there are 3 orbitals of lower energy, and therefore they occupy a separate orbital in the lower set. This is the case. and it is true for weak and strong both. It is not different for strong ligand and weak ligand. It remains same. D1, D2, D3. Strong and weak ligand doesn't make any difference in their configuration. But when we talk about D4 complex, there are two possibilities. See, if all the 4 electrons, they occupy lower set of orbitals, it means splitting is large. That means there is strong repulsion. And in case lower set orbitals occupy 3 electrons and 4th electron goes to higher set, that means it is the case of weak ligand. That means if delta O is large, then electron will try to remain in the lower set, and complex has less number of unpaired electrons, and therefore that is called low spin complex, inner orbital complex. And a repulsion due to pairing of electron, if it will be less, if delta O is small, then after filling lower set with 1 electron each, next electron goes to higher set, and in that case repulsion due to pairing of electron will be more than delta O. So if delta O is large, then the repulsion due to pairing, then pairing takes place. If delta O is small, then electron will jump to higher level. So that means pairing of electron will occur only after all the 5 orbitals are singly filled. So complex will have maximum number of electrons and is called high spin complex in case of weak ligand. And actual configuration adopted by the complex is decided by the relative values of delta O and P. What is P? It is the energy required for electron pairing, because when electrons paired up in the single orbital, then there is a repulsion between the electrons. So we have to work against repulsive forces to pair up the electron, and that energy is called P. So if P is large, then pairing does not take place. If delta O is large, then pairing takes place. So see, when delta O is less than P, that means to shift the electron to Eg, energy required is less, and to pair up the electron in T2G, energy required is more. So in this case, obviously it is a weak field because delta O is less. So obviously 4th electron will jump to the higher level, that is Eg, and therefore configuration becomes T2G Eg1, and it is high spin complex, or inner orbital complex or outer orbital complex. It should be outer orbital complex because all the inner orbitals are having electron. If delta O is more, that means there is a strong field, means ligand is strong. So in this case, to shift the electron to higher level, energy required is more, and to pair up, energy required is less. So in this case, pairing will occur in T2G orbitals with Eg orbital remains unoccupied, and that's why configuration is T2G4. So inner orbital will be used, so it will be a low spin complex and inner orbital complex. See, if delta O is high, so see, electron is paired up in the lower orbital, so configuration is T2G4. Strong ligand is there, complex is of low spin. If delta O is small, then electron will shift to higher level, and therefore Delta O small means weak field of ligands, and complex has high spin. So strong field ligands form low spin complexes, and weak field ligands form high spin complexes. So tell me, which of the following is or are strong field ligands? Yes, beta. Beta, chloride, iodide, halide, all the halides, including water, is a weak field ligand. Okay. It is carbon monoxide, CO, and cyanide. These are strong ligands. Okay. So answer is B and C. Which of the following is or are weak ligands? Yes, halides are weak ligands. Now, what are the limitations? So, one limitation we have discussed, that in case of, yes, very good, that's great. Okay, just limitation we will cover. Okay, consider ligand as a point charge or dipole only. It consider ligand as a point charge, and it does not take into account the overlap of ligand and metal, obviously, because there is no covalent bonding. Covalent bonding is completely ignored. That's why it does not take into account the overlap of the ligand and metal orbitals. And at the same time, it does not take into account the covalent character of bonding between the ligand and central metal. And it fails to explain the strength of ligand, because he considered the ligand as a point charge. So, CO is at the higher end. CO is strongest ligand, which is neutral. So, if ligands are point charges, then negative charges should have higher strength. It should be strong ligand. And see, all the halides are weak ligands. But neutral CO is a strong ligand, so it fails to explain, though it successfully gives that spectrochemical series arrangement, but it fails to explain the strength of the ligands. Like